So good morning to all of you MSc first year physics student. So today we want to see the lecture series on our subject is the quantum mechanics, and we want to continue our chapter is the angular momentum. So in the last of few lectures already see the idea about the total angular momentum and orbital angular momentum and how it is calculate the eigenvalue equation of the orbital angular momentum and total angular momentum. And due to depends on this equation, eigenvalue equation, we want to see our next point. So that is the matrix representation of the angular momentum. So in this section we are going to discuss, so that is the matrix representation of the angular momentum, and where this angular momentum, which is the operators of the eigenkets and operators that will be represented in the column, and the which is considered as the vector and square matrices, which is respectively, this is achieve the expanding states and the operators which is in the discrete basis, and after that we have to also see how the matrix representation of the orbital angular momentum. So since we have to know that is the your operator, so that is the total angular momentum j square and jz, which is commute on the set of their common eigenstate, which is j and m, which can be chosen as the basis. So you know that already we have to that calculate the commutator relation of the, that is the j square and jz, which can be chosen or which can be choose the common basis, and this basis condition we have to see here. Okay, so what is the relation of this common basis? So that is given for the orthonormalization condition, and for this the basis which is depends on the main condition, which is the bra and ket relation of j and m, and what is the resultant of this? So this condition, which is nothing but the, so that is the bra of j prime m prime. Okay, and this relation which consider as the j and m, and the resultant of this condition by the orthonormalization condition, so that is given by delta of j prime j and delta of m prime m. Okay, so this is by the orthonormalization condition, Okay, so that is the j prime m prime of bra of j prime m prime ket of j and m, which is nothing but the delta of j prime j delta of m prime m, and the completeness condition of this we want to see. So that is the completeness condition. Okay, and this completeness condition, which is considered as the summation of I is equal to, or which is considered as j is equal to running form minus j2 plus j, which is the ket of jm bra of jm, which is nothing but the identity matrix. So that summation, which is running form, so that is the j is equal to, so j is equal to, or which is the value running form, because we have to know that the total angular momentum, for example j is equal to 1, so that your m value which is running minus j2 plus j, so that's why here that m value which is running form the minus j2 plus j. Okay, and the relation of which is ket of jm and bra of jm, which is nothing but the I, and where I, which is nothing but the unit matrix. I is nothing but the unitary matrix. Okay, and we have to know that your j square and jz are the diagonalized is the basis of given their joint eigenstate, and this eigenstate which is considered as the eigenstate of j square and it is the relation of the bra of j prime m prime, bra of j prime m prime, that relation which is given with respect to that j square. So that is the eigenstate or eigenvalue equation of j square with kate of j and m, and the resultant of this relation, so that is bra of j prime m prime j square of kate of j and m, and this relation which is nothing but the h cross square j of j plus 1, j of j plus 1, and which is delta of j prime j and delta of m prime m. Okay, so this is the main basis eigenstate or eigenvalue equation of j square, and using of this equation we want to solve the matrix equation or matrix representation. So for example, this is given as a equation number 1. Okay, and second relation which is given as the kate relation of j prime of m prime with jz operates, okay, with jz which is operates on the j and m. Okay, and this relation which is nothing but the minus m h cross, or which is nothing but the h cross m delta of j prime j and delta of m prime m, and we have to the next equation number, so that is the equation number 2, and thus the using of this relation, so that is the matrix representing of j square and jz in the jm eigenbasis, and jm eigenbasis are the diagonal and diagonal elements. So thus the matrix representation, the matrix representation of j square and jz, j square and jz which is in the jm eigenbasis, in the jm eigenbasis. Okay, so this is the general introduction idea of the representation of the matrix, and these eigenbases are diagonal, and this eigenbasis, this eigenbasis is diagonalized. Okay, so this is the basic theory, and now since if we consider the operator j plus and j minus which is do not commute with are the represented in the jm basis, so we want to matrix that are not diagonal, the that is for example, so this j plus or minus, j plus or minus is not commute, is not do not commute with, is do not commute is do not commute with the, they are represented in the jm basis, and they are represented in jm basis. Okay, so we want to see the what is the relation of this jm basis. So that is the kth relation of j prime m prime, which is j plus or minus of jm, and this relation which is nothing but the h cross of j into j plus 1 minus m into m plus 1 minus m into m plus or minus 1. Okay, and the relation of this j of delta j prime or j delta m prime of m, and next relation which is considered as so that is m prime m, and which is delta j prime j and delta m prime of m plus or minus 1. Okay, and this is given as the equation number 3. Okay, and if we can infer this matrix of jx and jy cap, we can infer the matrix relation of jx cap and jy cap of. And what is this matrix relation? So that is given, or already we have to see in the last lecture. So that is j prime of kth relation of j prime m prime of jx of jm, and this relation which is nothing but the h cross by 2 in bracket of j of j minus m. Okay, so this relation which is this j of j plus 1 minus m of m plus 1. So this is for the j plus, and which is we have to know that j plus operator which is operates on this, so that your m value is nothing but the m plus 1. So this is delta of j comma m plus 1. And next we want to see that for the j minus operator, so this eigenstate value which is nothing but, so here jx which is given here, so that eigen value which is depends on the j plus and j minus, so that's why plus sign is there. So this plus into under root of j into j plus 1 minus m into m minus 1, and this relation gives that your delta j comma m minus 1. Okay, so this is the relation which is considered as the jx relation, and if we see the eigenvalue of the jx, or we can infer the matrix representation of, or that relation of the jy cap, and this relation which gives in terms of the eigenvalue or eigenstate equation, and this equation which is nothing but, so that is the kth relation of the j prime m prime of jy cap with jm, and this relation gives the h cross by 2 in bracket of j into j plus 1 minus m into m plus 1. Okay, and this rising operator which is nothing but the delta of j comma m plus 1. Again minus sign is there in under root of j plus 1 minus m of m minus 1, and this is representing the delta of j comma m minus 1. Okay, and by using this equation value we want to write okay. So we want to show the matrix representation and we want to solve the one of the example of depends on this. Okay, so first of all, for example, j is equal to 1. Okay, j value is given 1, so that is the angular momentum, that is angular momentum, so that is j is equal to 1. Okay, and if you have to know that idea, so that angular momentum j is equal to 1, so m value which is nothing but the 1, 0 and minus 1. Okay, so that is for j is equal to 1, so that m value is running from 1, 0 and minus 1, and we want to calculate. Okay, and if we see the joint eigenstate of the relation, okay, so that joint eigenstate, and this is nothing but this j is equal to 1 and m is equal to 1, so 1, 1. Again this j is equal to 1 and m is equal to 0, so that is given as 1 and 0, and again this j is equal to 1 and m is equal to minus 1. Okay, so this is the joint eigenstate. So we want to see this matrix representation of operator j square and jz, which can be inferred from the equation this 1 and 2. So we want to calculate the matrix representation of j square. So now first we want to calculate the matrix representation of the j square, and this is nothing but okay, or we have to know that idea, so that j square of j comma m is nothing but the relation is the h cross square under root of h cross square j into j plus 1 minus j into j plus 1, and this is j comma m. So this relation which used, so that is the j square is nothing but the relation which is taken from, so the first eigenstate, so that bra of 1, 1 ket of 1, 1, so that 1, 1 j square of 1, 1 okay. Next the relation of bra of 1, 1 j square bra of 1, 0 ket of 1, 0, and next relation which is nothing but the bra of 1, 1 which relation j square of 1 minus 1. Next which is given as, so 1 comma 0 of j square of 1 comma 1. Next 1 comma 0 which relation, so that j square of 1 comma 0, and next one is 1 comma 0 of j square 1 comma minus 1. Next one relation, so that is the bra of 1 eigenstate 1 comma minus 1 which is operates on j square on the eigenstate of 1 comma 1, then 1 comma minus 1 which is operates on j square is operates on 1 comma 0, and 1 comma minus 1 bra of this operates on j square is the 1 comma minus 1. Okay, and you know that already the matrix representation of this, so which is given in terms of, if we write here, how it is solved, that representation is here. So we want to calculate, so that is the j square eigenvalue or eigenstate or matrix representation. So here the ket of 1 comma 1, here ket of 1 comma 0, here ket of 1 comma minus 1. Okay, and here the relation bra of 1 1, bra of 1 0, and bra of 1 comma minus 1. Okay, so this is very interesting point to solve. How it is, we have to know that the relation h cross square j into j plus 1 of jm, or we have to know that the j value which is given as 1, and relation is the j square of j comma m is nothing but the h cross square j into j plus 1 of j comma m. Okay, so if we see, so this j comma m is what, 1 1, and this value is h cross square j into j plus 1, so 1 into 1 plus 1, so that is the 2, so this is twice h cross square, and j comma 1, so that is 1 comma 1, so this is 1 1 1 1 for only this condition, this gives the twice h cross square. Otherwise this 1 comma 1 is relation with this, so 1 comma 1 and 1 comma 0, we have to know that condition. So in both side we want to same eigenstate 1 1 1 1. If 1 1 is not there, so that condition is the this matrix representation which gives the 0 value, so that's why this is gives the 0 and 0. Again 1 comma 0 1 1 is 0, ket of relation 1 comma 0 j square with 1 comma 0, so this is nothing but the twice h cross square and again 0. Here 0 0, and relation 1 comma minus 1 and this 1 comma minus 1, this again also twice h cross square. Okay, and if we see this matrix representation which is given as the j square is equal to, in bracket of twice h cross square 0 0 0, twice h cross square 0, and again 0 0, twice h cross square. Okay, and that is if we taken to h cross twice h cross square in outside of this bracket, so this is nothing but the 1 0 0 0 1 0 and 0 0 1, so that the final matrix representation of this j square is nothing but, okay, is nothing but the twice h cross square of I3. Okay, or which is considered as the twice h cross square of I3, that I3 is nothing but the this is the unitary matrix. Okay, so in this fashion we want to calculate, or we want to see the matrix representation value of j square, jx, jy, jz, j plus or minus. So this value also seen in this type. Again we want to see the next relation, which is the, we want to show here the matrix representation of the jz. Okay, so that is the jz. how it is show the matrix representation, or you know that jz of j comma m is nothing but the m h cross, which is nothing but the m h cross of j comma m. Okay, and the matrix representation of this jz is nothing but the bra of 1 1, which is operates on jz, which is ket of 1 1, bra of this 1 1 of jz, which is operates on the 1 0, and bra of 1 1 of jz, which is operates on the 1 comma minus 1. Next relation, this bra of 1 0, this jz operates on the 1 comma 1. This bra of 1 0 or jz operates on the 1 0, and the bra of 1 0 of jz operates on the 1 comma minus 1. Again, this eigenstate relation with bra of 1 comma minus 1, which is operates on jz, which is operates on the 1 comma 1. Again, eigenstate of bra of 1 minus 1, this jz, which is operates on the 1 comma 0, ket of 1 comma 0, and this bra of 1 comma minus 1 of jz, which is operates on the 1 comma minus 1. Okay, this type of matrix representation is there, and we want to solve this matrix value. So what is the eigen value of this jz operator? So you know that this jz is of jm is nothing but the m h cross of j comma m, and for j is equal to 1, for j is equal to 1. Okay, and if we see the matrix representation of this, okay, so bra of 1 comma 1, sorry, ket of 1 comma 1, ket of 1 comma 0, and ket of 1 comma minus 1. Again, this relation bra of 1 comma 1, ket of 1, bra of 1 comma 0, and bra of 1 comma minus 1. So here h cross is there. So you know that, so this 1 comma 1 and jm, so that value, so bra and ket value is same. Okay, bra and ket value is same. So what is main condition? So your m value is satisfied. Okay, and if we see this bra of 1 comma 1 and this 1 comma 1, so that is nothing but this value is the h cross is there, and other value is 0 0. Okay, if here 1 comma 0, okay, and this operates on the jz, and for j is equal to 1 and m is equal to 0, so j value 1 and your m value, which is get 0, so this value is again 0 0 and 0, and here because of why, here m value is what, 0, here m value 0, or your relation m h cross, m value is taken 0, so that is the 0 h cross, so that is the 0 h cross. Okay, and again taken relation is 1 comma 1 0, so this is also 0, and this is m value minus 1 minus, so minus 1 value, so here relation the minus h cross. Okay, so this matrix representation in terms of, so that is the jz operator value, so which is nothing but the h cross 0 0 0 0 0, this is nothing but 0 0 minus h cross. Okay, and this is nothing but, so that is the jz value of H cross is taken outside, and the matrix of 1 0 0 0 0 0 and 0 0 minus 1. So this is the matrix representation of the ZZ operator. Now we want to, in the next lecture, see the how was the matrix representation of the value of j plus, j minus, or jx and jy, and what is the eigenvalue and eigenstate relation of this. And using of this eigenstate relation and eigenvalue equation, we want to calculate the matrix representation of the jx, jy, and j plus and minus. So thanking of you.